right. Welcome back. This is week 2 of CS50. By now, if you've dived into problem set 1, you've probably encountered at least one of these. So this is a photograph of an actual logbook of an actual, and in fact, the first known bug in a computer program. This was plucked, this moth here under the yellow tape, from the Harvard Mark II computer, the successor to the thing that's in the Science Center back in the 1940s. And an annotation was made that this was indeed the first known bug, literally, to be found in a computer, and apparently the term stuck. Next time you're down in DC, you can actually see that bug in our own Smithsonian, so realize that it has entered our own nation's history here. But your own bugs are perhaps a little less worthy of enshrining, but you will get better this week and beyond at tackling these new topics. So a very rapid review of some of the syntax we looked at last week, and then we'll dive into some actual examples. So this was representative of a pair of Boolean expressions and softball question. The double vertical bars just denoted what type of Boolean. So ORing two things together. So either the thing on the left has to be true or the thing on the right. And if so, then you will, quote unquote, do this. This, by contrast, was a Boolean AND, which meant both left and right had to be true. We saw similar constructs in Scratch. And then we introduced conditions as well. So you can have one fork in the road, 2, 3, 4, any number really. But if you kind of extrapolate mentally from some sample code like this, you can imagine perhaps this getting a little unwieldy once you have 5 or 6 or 7 or so forth conditions. So it turns out there's another alternative syntax that functionally achieves exactly the same thing. And this indeed is consistent with this reality in programming that you can do almost anything in multiple ways. This is the so-called switch statement. And we'll see that it's actually a bit more limited than if, else if, because every one of the cases can only, as we'll see, be an int or a char, essentially. You don't want to use other data types, but it simply allows you to enumerate in a slightly more human-friendly way several different cases that you might want to apply. And then lastly, last time, we looked at loops. And we looked at perhaps the most syntactically complex one here, this for loop. And if you looked up during the music a bit ago, you'll see that Foxtrot cartoon, which actually was playing off of this idea of a for loop. A for loop has 3 segments where you can initialize some variables, a condition that you check every iteration, and then one or more updates that happens at the end of each iteration. But we also have while loops, which are a little simpler, but you need some way of breaking out of them, potentially. So we'll see examples of those. And then lastly, and this is the one where maybe your curiosity should be piqued just a little bit, that might come in handy, in particular with pset 1, where you want to do something and then maybe do that same thing again and again and again. For instance, this is a very common snippet of code to use if you want to prompt the user for some input, and they might be difficult. They might type in a negative number. They might type in monkey, as I did last week. And you want to again and again tell them to do something until they've satisfied some conditions. So we'll see this construct in action as well. So without further ado, let me go ahead and pull up the CS50 appliance here, and this is a buggy1.c program. So if you're following along at home or on your laptops, this is included in today's PDF and zip file. But this is indeed a buggy program. It's supposed to print out 10 stars on the screen. But why does it not, in fact, print 10 stars? And what does it actually print? OK, so 11. So the consensus is 11. Why is that? So this is the sort of mistake that should hopefully get easier to spot. We're starting counting at 0, and that's sort of good form, though not strictly required. The problem is, though, that we're counting up to and equal to 10. So if you just start counting on your fingers, that means this loop is going to iterate for I equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's actually my 11th finger, and so that's indeed one too many stars. So an easy fix here might be what? And just make it less than 10. You could just delete this. If you really wanted to, you could do something like this. But again, the former is probably preferred among programmers. Just to, by convention, start at 0. All right, so that's buggy1.c. Let me go ahead and open up another one here. This one is supposed to print 10 stars, 1 per line, but it does not. What's the bug here? Yeah? Exactly. So the line break needs to either be inside of the first printf here so that it actually gets applied again and again after every star. Because even though I've indented in this nice pretty way, remember that any time you have a condition like a for statement or a while statement or an if statement, if you have one line of code, you don't need the curly braces. If you have 2 or more, you do. So it doesn't matter how nicely you indent things. You could also fix this problem by including that curly brace there, another one here for good style. Let me go ahead and move the cursor back where it belongs. And this, too, would work. So again, another example of two different ways to do it. Which one might you prefer? The one-liner is kind of nice, to be honest, putting the \n right after the star, because you don't need the curly braces. You don't need a second line of code. You don't need to call printf sort of foolishly twice. And so there's multiple ways, again, to do something like this. All right, how about one more here? So let me go ahead and open up buggy 3. And in this case, I'm going to just defer this, because I was not supposed to open buggy 3 at this point in the story. So we'll come back to buggy 3 there. So buggy 3 is going to be pretty damn interesting. So let me go ahead instead and open up something else just as a sort of warm-up here. And again, raise your hands or look confused as visibly as you can if you have any questions, and we'll pause or slow down at any point. So this is a really stupid program. It computes the total of two numbers mathematically, but that's it. And I point this out because, one, it's actually syntactically correct, but when I try to compile this, I'm not sure GCC is going to like it. So notice the familiar now, include standard io.h. Now, technically, I don't even need that because I'm not using printf here. So this really is a useless program. So I've got int main void, and that's just copy-pasted from last week. Now I'm declaring x as 1, y as 2, and z as x plus y. So that actually looks pretty reasonable. I'm declaring variables on the left and assigning them values on the right. But let me go into this directory, and I'm going to go ahead and type make math1. And unfortunately, GCC is yelling at me. Error, unused variable z, then some crazy looking -w thing, all warnings being treated as errors. Well, what's going on here? Yeah. Yeah, exactly. I may very well have computed z, and it's correct. It is the sum of x and y. But what was the point of this whole exercise? So one of the features of GCC that we've enabled by default in the interest of pushing you toward correct code, as well-designed code as possible, is to yell at you when you do something that's just a waste of time. If you're not actually going to use z, as you might by using something like printf. Printf percent, what would it be for an integer? %d for an integer, maybe \n for good measure. Now this might make the compiler more happy, because now I'm not only declaring z, I'm using z, even though the program itself is still underwhelming. But if I now go back down here, let me zoom in and rerun make math1, now it's indeed happy. And if I go ahead and run math1, I get back the answer 3, which is, of course, 1 plus 2. So just to point out this error message that even when you see things at first glance that look a little cryptic, just read into at least the part that, frankly, does not look overwhelming, and see if you can't infer where the error is. In fact, if I go ahead and break this again and delete the printf, let me zoom in and recompile math1, notice that it's actually being a little more helpful than spitting out this message here. Unused variable z, yes, but it's actually telling me, GCC, that it's in math1.c that I screwed up. It's specifically at line 19, and then somewhat less usefully, specifically look at character number 9, give or take. So 9 characters into that row. So it's actually pointing you toward what's probably the error. Now realize this isn't a golden rule. If you actually have multiple errors, you might actually be informed that you've got an error at line 15 when actually it's on line 14 because you've done something wrong above it. So sometimes the compiler can get confused. But again, look for these clues as you try to diagnose these initial bugs. All right, so let me open up math 2, which is now trying to do a bit more. So in math2.c, I actually am fixing this problem. So we already did that. So you have a copy of the correct code there. In maths3.c, we're going to go ahead now and use a floating point. But this, too, is actually a little broken. So let's take a look at the code. I've got standard I/O for the sake of printf, int main void, so that's boilerplate. And now I'm doing float answer. So a float, just as a recap, it's how many bits? So it's 32 bits. It's not the biggest possible floating point value, but 32 bits is still a lot. Surely we can represent something as relatively small as 17 divided by 13, which should be 1 point something. You would like to think that 32 bits is enough to represent the number 1, give or take. But then I go ahead and divide 17 by 3 here. I store the result in answer, but I'm then printing it out, .2f. The .2 denotes what? So just 2 decimal places. %f generally means give me a floating point value, but .2 means only show me 2 numbers after the decimal point. What am I plugging in answer? So this actually feels OK, but let me go down here now, and let me zoom in and run make math3. It does compile OK, but when I now run math3, I'm pretty sure 17 divided by 13 is not 1.00. Frankly, I don't quite remember exactly what it is. Pretty sure it's not 1.00. So what's going on here? What's the problem? Yeah?
You're dividing into integers, so you're getting an integer answer that's then being converted to a float.
Yeah, so this is something we haven't talked about explicitly, but indeed when you divide two integers in C, what do you get back? Well, you're going to get back an integer by nature of mathematical operations in C. So 17 is an integer. Why? Well, it's obviously an integer, but more specifically, it does not have a decimal point in it. So C views 17 as an int. 13, meanwhile, also looks like an integer. There's no decimal point, so it too is treated as an int. And that's actually a bit of a white lie. It's treated as a long typically, but the results are the same. It is not considered a floating point value. So 17 divided by 3 gives me 1 point something. Well, that something can't fit into an integer. It can't fit into an int, and so the point something something is just thrown away. This is called truncation. So the number is just truncated, and you lose that. So even though I'm then taking the answer, and I'm saying it is a float, it's too late. You've already thrown away everything after the decimal point when you did the original division. So if the problem then is that answer, even though I'm calling it a float, is actually storing the result of an integer divided by an integer, whose result is an integer, how do I fix this? Yeah, and back. Yeah, so I can actually introduce this other feature of C known as typecasting, or more succinctly, to cast a variable from one data type to another is to cast it. So what you can do is with simple parentheses, you can do something like this. Yes, 13 is actually written as an integer, but I would like the compiler to treat it as though it's a float. And this is actually legitimate because you're not converting apples to oranges. You can reasonably convert an integer to a float. You just add a decimal point, essentially, 0.00000. So now this is effectively 17 divided by 13.00000, albeit with some imprecision. So now when the division happens, I get back a float. I'm storing that float in a float called answer. And so let's see if my answer is now any better. To make sure to save always with Control-S, or the File menu, let me go ahead and recompile Math3. No errors, that's good. And let me go ahead and rerun Math3, Enter. Ah, that's the number I was hoping for. So this might be sort of low-level detail, but this is absolutely going to be important, even in pset 1, where you're, for instance, trying to provide a user with change, and you're dividing some total amount by 25 cents or 10 cents or something like that. You're going to need to beware or be mindful of these kinds of issues that you might literally be throwing pennies away. In fact, if you think now, if you've ever seen the classic Office Space or the precursor Superman 3, you might recall that the scam that they waged in Office Space was to kind of skim the fractions of pennies off of the dollars that were going through Initech, the company. Well, this actually relates, right? Those guys were programmers, and what they were referring to was, one, this inherent imprecision of floating point values that we saw last week, and also the fact that sometimes these remainders are just potentially thrown away. If you've never seen this movie, I do recommend. Yeah? Good question. Why do you have to cast the 13 as a float and not the 17? Well, first, it suffices to only do one of them. So that's fine. And notice what happens here. If I do this and save, then recompile with make math3, and then rerun, so that actually would fix it as well. I just chose one arbitrarily. I could do two, and frankly, there's an even simpler approach. You could certainly just avoid this whole new concept of float, of casting rather, and just say, fine, make it 13.0 and make this 17.0. That might work as well. Yeah? So you can. It looks a little weird, but you could also do this. C is perfectly content with that if you just like the elegance of no trailing zeros. Any other questions on floats? Yeah?
Before you had done the typecasting, so is answer a float or an int?
It's a good question. So before we did the typecasting, is float an answer or an int? It is a float because we explicitly made it a float, but it was assigned an integer value. So what happens there is actually called implicit casting or implicit conversion. So it is indeed a float, and conceptually the point 0 is just appended to it when the equal sign moves the value from right to left. And a question over here? Yeah? No, only one of them needs decimal places. So essentially the sort of more powerful number takes control. So a floating point number with precision, with a decimal point, sort of supersedes the weakness of an int. And so you just need just one of them. So again, the takeaway here is not that the next time you divide one constant value by another, you should be mindful of this, but rather when you're taking arbitrary user input, maybe dollars and cents, these are the kinds of issues you need to be careful of. And certainly in the real world, if you're the person implementing the next automated teller machine, these are absolutely the kinds of issues you need to be mindful of when dealing with any kind of currency and fractions thereof. All right, so let's transition now to this file here. This is a file called non-switch.c, just to convey the idea that it's actually not using a switch. Let me scroll down just a little bit here and see if we can't read through this program. At the very top, I'm using the CS50 library, standard I/O. So that's a hint that I'm probably using printf. I'm probably using getInt or getString, something from CS50. And now here's my main routine. And the comments kind of reveal what's going on here. So in that first line, I'm asking the user for an integer. Notice that just aesthetically, I'm not using a \n at the end of the line. This is purely a stylistic decision. I just want the cursor to blink to the right of the prompt rather than put it on a new line. But that's not strictly necessary. The next line we used last week, int n gets getInt. So that's relatively straightforward now, hopefully. In future weeks, we'll actually look inside of getInt as to how it's working. But for now, you're welcome to be blissfully content just assuming it gets an int and hands it back to you. So now we're finally using Boolean expressions in C that are actually using the AND expression here. So in short, this seems to be a simple program that says if the user inputted a number that's between 1 and 3, go ahead and tell them you picked a small number. Else, if it's between 4 and 6, you picked a medium number. Else, if you picked 7 through 10, it's a big number. And anything else, negative, 0, something huge, it's going to say you picked an invalid number. So here, too, just to point out an FAQ or a common mistake, realize that when you AND two things together, you don't necessarily want to say, for instance, if n is greater than 5 and n is less than 4, do this. Because if you just think through that logically, make sure that the two ranges you're comparing are actually inclusive and not something that's greater than 5 and less than 4, which is obviously impossible. So just think about if you're ever running into a bug where you're using these Boolean expressions, just consider what your actual logic might be. So this is starting to feel a little ugly, right? I've got 4 different conditions. It's a little hard to read with all the ands and the greater than equal signs. And just to be clear, to express the notion of greater than or equal, on paper, you would say angled bracket and then the line under it. There's no such key on the keyboard. So the convention is angled bracket and then an equal sign. 2 separate characters with no space. So let me improve this, debatably, with switch.c, non-switch, switch. Let me go ahead and improve this as follows. So rather than do this, I could actually say switch, and then what do you want to switch on? Well, whatever the value of n is. And now I've got some placeholder text here, and what I can start to do is say, all right, in case 1, do this. And then I'm going to steal my text from down here. You picked a small number. And then I'm actually going to do this. I need to say break. But then I can do this. Whoops, don't do that. Then I can do this. I'm going to go up to 4. We'll come back to the ones in the middle. You picked a medium number. And then I'll do one more for good measure. Case, let's see, I think it was 4, 5, 6. So 7 was the next one. You picked a big number. And then just to make sure I capture every possible scenario, I'm actually going to have at the very bottom here what's called the default case, where you picked an invalid number. And then I'm going to close the curly brace. So again, we'll fix the fact that we're skipping 2 and 3 and 5 and 6 in just a moment. But this is just another syntax to achieve exactly the same thing that doesn't have all of these angled brackets and such. Instead, the switch statement says, look at the value of n, and then check this list of possible cases. And whichever case actually applies, go ahead and do that one. And only that one. So I can actually now round this out. You can have multiple cases. I can say case 2 and case 3. Down here, I can say case 5, and I can say case 6. And then lastly, down here, I can say case 7, case 8, case 9, and I think I had 10 before, so case 10. And that's it. So arguably, this too is now starting to devolve in something a little messy, but at least it's a little more skimmable. Rather than have to parse something visually that's kind of a big jumble of text, it's pretty wide, it kind of requires more thought. What's nice about switch statements, just as a feature of the language, is that bang, 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 you can see what the applicable cases are. So just realize this is an option, but the only gotcha is that what you switch on generally has to be an int or has to be a char. There's a couple of other things you can use, so it's somewhat limited. Yeah? Exactly. Case 4 or 5 or 6 are all going to do the same thing. They're going to say you picked a medium number. But this fact, I've introduced, notice, this new keyword break, which you can actually use in loops as well. Notice what happens if I don't have that break. So I think I got my syntax right. I'm going to go ahead and save this in my terminal window down here. I'm going to go ahead and make, this is still called non-switch, even though we've changed it to a switch. Compiles OK, so that's always a good sign. Non-switch, give me an integer, let's say 5, you picked a medium number. Let's say 1, you picked a small number. Let's say monkey, retry. So that's the CS50 library catching that. 0, that's my own program catching that, saying it's an invalid number. But notice what happens if I forget this break statement, which literally does what it says. Break out of this chunk of code. If I forget this, and I forget this, whoops, not that. If I forget this, and this one, leaving out the breaks, which is easy to do, and now recompile my code and make non-switch, and then run switch and type in 1, what's happened here? Right? This is absolutely a bug, but that's because, again, C, being a computer language, needs to be told exactly what to do. And what these case statements mean is the instant you match one of these cases, the code just starts executing everything you've written below it, and only once you hit type break, semicolon, does it break out of the whole switch statement. So this is both an advantage sometimes and a disadvantage. An advantage in that we can consider multiple cases, but a disadvantage if you leave out that break. Strictly, it's not necessary to have a break under default, but perhaps as a matter of good style and consistency, it's good to have it there. But it does need to be at the bottom. Yeah?
It does seem odd that it displays all of them, even though the value of n doesn't change. What about the way that switch works makes that the case?
It's a good question. So what is it about switch that makes it the case that all 4 of those outputs are printing? It's literally the definition of switch. When you match a case, start executing code until you see break. So the subsequent case statements are ignored. So the compiler is smart enough to realize, oh, I've seen case, I've seen case, I've seen case. But until it sees break, it's going to keep executing everything that I happen to have indented here. So it's just the definition of the statement. Other questions? Yeah, in back. Good question. Is there a way in a switch to consider a big range of numbers? No. You need to go back to the if condition and your use of greater than or less than if you actually want to consider a range. So you wouldn't want to use a program like this for 1 to 100 because, frankly, then the switch implementation would just be messier and uglier and much longer than the corresponding if-else approach. So again, just another tool for the toolkit, another way in which you can solve these kinds of problems. So let me go ahead now and open up one more example here. So this one is called positive1.c. And it's the first version of a little program that actually uses that feature of a loop called do while to actually prompt the user again and again and again, especially if he or she is being difficult. So there's a couple of interesting nuances here, though. So notice first that, again, the program starts in a familiar way with these 2 libraries and a bunch of comments up top. Int main void is the same as usual. But now notice a couple of new things. So 1, do, and then notice there's nothing parenthetically to the right. It's just do and then open curly brace. Because what's interesting about do while is that these lines are always going to get executed no matter what. So it's an opportunity to do something before you even check some condition. But at the bottom of the loop, you're only going to do it again if that condition checks out. So in other words, if the user here provides a number that's less than 1, I'm going to go through the do chunk of code not only the first time, but again and again and again until the user finally cooperates and gives me something that is not less than 1, like 2 or 3 or 4 or 1 itself, at which point the loop will terminate. And then it's finally just going to say, thanks for the 2, or whatever it is I typed in. So just to be clear, let me go ahead and run this at the bottom here. So this, again, is positive1. So make positive 1. And I'll zoom in. Enter. Compiles OK, +1. I demand that you give me a positive integer. I'm going to give it -1. It's going to do it again, -2, -3, -100, 0. Still not cooperating, but if I finally give it 1, thanks for the 1. And this is a way, again, of maybe in, say, pset1 actually doing something again and again. But notice what I did. What's kind of interesting about my declaration of n here that I've not done in past examples? Yeah, I kind of declared it up top. And this was why I think we proposed this last Friday as an option, but then decided, just do it all at once because it's more elegant. Right? Every example thus far, we've not had int n declared way up there. We did something like this. But this introduces a problem now. So n is clearly a number that I want to use in this program. Not only getting it inside of the loop, but I want to use it, obviously, in the printf at the very bottom of the program. But here's a gotcha of C. When you declare a variable, it only exists within the confines of the most recently opened curly braces. Those curly braces define a buzzword called scope. So int n, as declared here between those curly braces, only exists in your computer's memory while you're executing code in between those two curly braces. The moment you pop out of that loop, for instance, at the very last line, n is gone. The RAM, the memory that it was occupying, those 32 bits, have been taken away from you, reclaimed for some other random purpose in the computer, and you no longer have access to those bits. And thus, n is out of quote-unquote scope. So what you'll see if you make this mistake is the following. Let me go ahead and recompile now that I've saved this file with make +1. And already, there's a whole bunch of errors. Again, this shouldn't necessarily mean you've made a whole lot of mistakes. You made one that actually has a ripple effect on the rest of your program. So what's going on? So first of all, look for the first sort of reasonably phrased line. All right, so in function main. That's apparently where my issue is. This denotes line 22 of +1.c, unused variable n. So this is the error we saw before. And it is unused now because I'm declaring n inside those curly braces, but then I'm not using it. It's like z in that silly example earlier. But there's something more here down here. Then it's saying, confusingly, on line 24, which is down here, n undeclared, first use in this function. So GCC is being consistent with this story. The moment you exit those curly braces, n is gone. So on line 24, at the bottom of the program, n no longer exists, and so the compiler recognizes as much and yells at you and doesn't even let you compile or run this program. So to just roll back, what's the fix here? What's the solution? Yeah. Quite simply, you declare n outside of the scope of that loop. And even though, frankly, it looks or might start to feel a bit ugly to kind of put this variable in no man's land up there, that is indeed the correct solution. It's still inside of main, so that means every part of main has access to it, including inside of the do loop's curly braces, but at least now it's within scope for the entire function. Now, just as a teaser, technically, and those of you with prior programming background, and especially in Java, might be in the habit of putting what are called global variables, where you declare variables outside of main even. The advantage of this, as we'll see in future examples, is then every function you write, not just main, you can write your own functions, just like you can write your own scripts in Scratch. Every function you write will have access to n, but this is generally considered very bad, very messy practice. So we'll come back to this, but for now, the correct solution is indeed to put it right inside there, outside of the loop. Yeah?
Is there any way you can, like, so let's say the user puts in, like, -1, and then it, like, will print something like try again, instead of, like, just repeating I demand that you give me a positive?
So you could. So if you wanted to have a more specific yelling at the user, like that is negative, I don't want that, or some kind of informative message, absolutely you could do it, but you'd have to redo this loop. The advantage of a do-while loop is that if you're content in just saying the same thing again and again, I mean, look how easy it is to do that. But the downside is you can't provide more informative messages like, that's 0, or that's negative. To do that, you're probably going to want to introduce some if conditions inside of the loop, and maybe even not use a do-while, just use a while loop or a for loop, as we'll soon see, and yell at the user appropriately. Yeah?
Is there a way to destroy a variable within the scope of a program?
Good question. Is there a way to destroy a variable within the scope of a program? No, but we will have that feature in PHP. And back. Does n have a default value? Short answer is it depends. We'll come back to that before long. So for now, assume that if you do not give a variable a value, it's going to contain what we're going to call literally a garbage value. It's going to contain some unknown value, and indeed that's the common case, for it to be some piece of junk, some random pattern of bits that just so happens to be there. Let's go here.
In your while condition, you had like many things, many categories, so if you want to just fit your variable.
OK.
Is there any limit on like the number of logical conjunctions that you can use?
Good question. Is there any limit on the number of logical conjunctions you can use in this parenthetical here? If you wanted to say while n is less than 1 or n is greater than, say, 99, if you want it to only be a digit from 1 through 99, no, you could keep oring things together, anding things together. You might want to use parentheses to make sure the logic is all correct. The only limit really is on readability and what a reasonable programmer would sort of be comfortable with or yell at you at if it's just becoming unwieldy, frankly. All right, yeah?
Within the same level of scope with the curly brackets, can you keep reinitializing a variable?
Yes. Within the confines of the curly braces, you could keep reassigning n a value in different lines of code again and again and again. That is perfectly correct. The only thing you don't want to do, as we discussed on Friday, is you don't want to redeclare that variable by saying int again. Once you've declared it, stick with it. Don't specify int on the left-hand side again. So here's a slight variant of this. So this is a version called positive2.c, and it's example now of introducing a Boolean variable. Bool is not a type in C that's built into C. It does exist in C++ and PHP and other languages, but the CS50 library gives you access to a Boolean data type that's just true or false in lowercase. And notice that just with this modification, you can actually make the code a little more readable, a little more like English. So at the top here, I've this time declared a Boolean called thankful, just because I want it to sound kind of cute and read like English. And I'm initializing that Boolean value to false. And again, false is in all lowercase. Then I've got a do loop, and I've got printf, I demand that you give me a positive integer. And now notice a difference in this program is I am getting an int from the user, but what am I doing with it? I mean, really nothing. I'm comparing it, so I'm kind of using it for something, but I'm throwing that value away as soon as that line of code is done executed. But in English, those two lines, if getInt greater than 0, thankful equals true, what's the implication? Well, it just means that this program is meant to be thankful when the user finally provides it with a positive number. Now, why is this useful? Because now in my while condition, inside of those parentheses down here, now we can introduce another piece of syntax, namely the equal sign, that says, well, while thankful is false. While I'm not thankful, do this loop again and again and again. We've seen Boolean expressions before. If you have a greater than sign or a less than sign, right, just logically, that's going to evaluate to a bool, true or false. X is less than Y, true or false, yes or no. Well, you can literally put a Boolean value there like thankful and compare it against a Boolean value like false or quote unquote true to express the exact same thing. But we can do this slightly more elegantly, but we should first tease apart this. Why am I doing equals equals instead of equals, do you think?
The equals equals compares the value of thankful that we get, which is the new value of thankful after it starts to reduce.
Exactly.
False, whereas when you say thankful equals to, it assigns the value of thankful.
Exactly. So if you think back to what single equal sign means, this is the so-called assignment operator. Now, I might keep saying equal sign, but in programming, this is the assignment operator, and it puts the value on the right into the thing on the left. Now, the problem is the world kind of painted itself into a corner, because the first time someone needed to write a program that needed to express the comparison of two values, where in English or in math we would say equals to compare two values, kind of out of luck, because we already used the equal sign on our keyboard to denote assignment of values from right to left. So the world decided that, well, fine, let's just put two equal signs. So equals equals does an actual comparison. Equals does a single assignment. So realize what could happen here. What if I accidentally do this? And this, too, is a very common mistake early on. This code will compile, but what's going to happen now? Exactly. This mistake, stupid as it is, this one character I made the mistake with my keyboard, is automatically, every time the while condition executes, it's going to assign to the variable called thankful what value? False, and then it's going to evaluate it. So again, just like in math, order of operations, the stuff inside the parentheses happens first, then the big parentheses themselves happen. So thankful gets a value of false. Then the question is asked, well, while false, well, what's going to happen then? Well, false is false, which means it's going to break out. So in other words, if you have while thankful gets false, this thing is never going to loop more than once, because no matter what the user does, as soon as you hit the while condition, thankful is going to get a value of false, and bam, the while loop's not going to repeat itself, because again, it only repeats if it is true. All right, so one last example here. Let me scroll down to, let's say, +3, just to introduce one more piece of syntax. For those who remember what the previous example looks like, what's the one difference in this program? Yeah, so there's this new piece of syntax, the exclamation point, otherwise known as bang in programming. And bang thankful here just means not thankful. It inverts the value of a Boolean expression. So I actually don't need to be so verbose. I don't need to say while thankful equals false. I can instead just say, more idiomatically, while not thankful. And that's how you would pronounce that, not thankful. And it just inverts whatever the thankful value is. So just logically now, you can read it quite easily. Do, print that, get an int from the user, while you're not thankful. And you're only going to become thankful when the user does what? Final sanity check? Gives you a positive integer. That's it. So again, 3 different ways this time that we've done something. But what's nice now is that we have the ability to express ourselves with just slightly new pieces of syntax. But these programs are somewhat underwhelming to run. Let's add something that's just a little graphical now. So here's one other example called progress. Progress1 actually introduces another header file and another function that you won't generally use, but it does hint at fancy features to come. Notice that because I read the manual, turns out I was told to include unistandard.h, that header file, if I want to use a function called sleep. And you can probably guess what sleep does. It puts the program to sleep for 1 second in this case. So what does this thing seem to do? Well, it's apparently going to simulate progress from 0 to 100%. So notice this is not a bug this time. In my for loop, I deliberately want to go from 0 to 100 because I want to count from 0 up through 100 in this case. And apparently, it's going to print on every iteration %complete, %d. That's an integer. We're going to plug in the value of y. And now this looks a little cryptic, but take a guess. Why do I have %d, %%? Yeah, exactly. So this is what we generally call escaping a character. Here, too, it's one of these painting yourselves into a corner. If you have decided as a world to use % to mean here comes a format code for printf, like %s, %d, %f, well, you're kind of out of luck if you want to actually say %, because the compiler apparently has been trained to know that anytime you see %, another letter is going to come after it. But if you want a literal %, the way of doing that is to say %%. Now you can imagine this actually becomes messy. How would you do %%? %, right? Or 3% is 6%, 4% is 8%. But thankfully, this is not a common case, right? Odds are this is not a common program to write, so the world just made a judgment call that, fine, that might happen, but it's very rare. So what's this actually going to do? It's going to print 1 per line, once per second, this kind of progress bar. So let's try this. Let me open up a bigger terminal window here so we can see more at once. And let me compile progress1. It compiles OK. And again, to be clear, all I did was I opened the separate program that's called terminal. It's this little black icon there. And it just lets me do the same thing full screen, just so it's a little prettier. Enter. All right, so it's getting interesting, right? You can really see and feel this for loop. Frankly, I'm already getting a little bored, so why don't we go ahead and hit Control-C to kill this program. But let's assume that it's actually going to go up through 100, which it should, because according to the code, we have less than or equal to 100. But this is obviously not a very user-friendly progress bar, right? It'd be nice if just the number updated itself. But notice the takeaway here. Printf is pretty limited. Printf is kind of like an old-school typewriter. Once you type out a word and do \n, enter, that's it. You can't really scroll back and change what you typed because it's already emblazoned on the page. So in this case here, it'd be nice to somehow more elegantly just change the % sign. So we can actually do that. Let me go ahead and open up version 2 of this, progress 2. Now it's a little fancier because I had to fix a bug, but notice the difference now. What am I actually using to print out the %? I'm not using %, \n. I'm instead using what? So %r. So this is one of these silly computer issues we'll actually trip over multiple times during the semester. Long story short, in the world of Unix and Linux, these older operating systems and modern operating systems that are mostly command line based, but just like the appliance that nowadays do have graphical environments, the world decided that to end a line in a text file, in other words, when you hit enter, what actually goes in the file? Well, it was \n. Now, unfortunately, the folks at Microsoft decided years ago that when you hit enter on your keyboard, what actually gets saved in the file? It's not just \n. It's something called \r \n. So 2 characters get saved in the file. Those of you who actually remember typewriters might know that in a typewriter, the old mechanical thing, when you hit enter on the keyboard, not only does that scroller kind of scroll this way, also the printing head moves back to the left. So that's what Microsoft was being consistent with. \n moves the roll thing upwards, and carriage return, CR, \r, moves the head back to the left of the screen. So technically, Microsoft is kind of implementing the old school typewriter the most accurately. But then Apple came along and decided, to hell with you, we're only going to use \r. So we have 3 different operating systems, major operating systems, 3 different ways. And this is thankfully mostly irrelevant, except when you try to open a file that you created on a Mac on a PC, a text file, or when you open a file on a PC that you created on a Mac, or a Unix or a Linux machine. If you've ever opened a text file, on Windows in particular, with notepad.exe, and even though it's supposed to be a lot of text, it's all on one crazy long line, that's simply because Notepad expects \r \n, and if it doesn't see it, which it might not if you made it on a Linux computer or a Mac, all together, you're just going to get some big mess. WordPad, by contrast, if familiar, knows about just \n. So long story short, we'll come back to that with web programming. But for now, we're taking advantage of this as follows. \r has the effect, conceptually, of moving the head the printing head back to the left without doing what? Moving to a new line. So it just moves the printing head back to the left. So the effect now is that on every iteration, I'm going to reprint %complete : and then a number. But because I'm printing the same exact words and only changing the number, we have sort of a nice simulation of animation here. If I make progress2 and run now progress2, notice that we actually have a fairly pretty looking implementation now of a progress bar that's still a little slow for our tastes, but now we're exercising more control over the screen. Now, can we do a little better here? This last version of progress, if I go in here down to progress3.c, notice that I can do this also in a different way. So how am I doing this differently? Before I did a for loop, and frankly, I would say 8 times out of 10 when I write loops in any programming language, I typically, by default, use for loops. Even though they're a little uglier, they let you express yourself a little more succinctly. But we can do this otherwise. I could declare I as an int up here. I can then say while I is less than or equal to 100. And then what do I have to do? On each iteration, I can actually manually increment I with this ++. So again, I would actually argue this is a little messier of an implementation, because look, I have I at the top, I've got this I++, and again, recall what I did a moment ago. This just feels a little more compact. Everything's more tightly knit. But again, this hammers home the point that you can implement these things in many different ways, just as in Scratch, with different pieces of puzzle pieces. Any questions? Yeah? Uh-huh.
Will it show 300%? Like when you go back and
Oh, yeah. Say it once more.
Will it show 300%, or does it like erase the?
Oh, good question. So I'm actually kind of cheating and making this seem a lot easier than it is, because the numbers I'm printing are actually going up from 0 to 1 to 2 to 3 to 100. They're getting bigger. If we actually count it in the other direction, you can see what would happen here. Let me go back to progress2. Let me actually initialize this to 100. Let me go ahead and say this should do this while I is greater than or equal to 0. And what do I want to change this to? Minus, minus. All right. So same idea, just slightly different syntax. Let me recompile this. Let me rerun it. And now you can't quite see it because my cursor's there. Let me rerun this again. I'm going to cheat just so you can see what's going on. I'm going to put a couple spaces at the end so that my green cursor is not overlapping. So if I rerun this, now notice that No, that actually fixed. Oh, I can't do that. I just fixed the problem by adding those spaces. All right, so we're going to have to look through my green cursor here to see this in this particular program. So notice what's happening. If the projector cooperates, that's a bug, right? So the green cursor is just an artifact of the GUI program. But I should not still have a % there, but I do, because why? The number used to be 100. Now if we and there was thus a 0 previously there. And so now we have a % overriding part of that big number, but not all of it. So if we let this actually go down monotonously down to 987, we'll see what also? Yet another % sign. So in short, I kind of cheated here to make it seem easier, but we could fix this obviously by just hitting the space bar or some other trick. But by default, the line is not erased. It only prints out what you tell it to do. All right, why don't we go ahead here, because it's a lot to digest. Why don't we go ahead and take a 2-minute break. I'll let this count down, play some music, and then we'll resume. All right, we are back. So as promised, bug, 3% signs was not the desirable outcome. Know that we could address this in a couple of ways. One, there's the slightly hackish approach where I just hit the space bar a few times. But you can actually do better. And just to plant a seed, know that just as with %f, where you can specify how many numbers should follow the decimal point, also with %d, you can do what's called specifying the width of a number, how many spaces it will take up, even if it doesn't need that many digits. So long story short, know that with printf, for which there's documentation online that I'll pull up in a moment, there are these additional format codes and tricks so that you can tell printf, make sure you're using at least this much space, even if you don't need it for the size of the number. Yeah? And the f+2 is the other loose end here. So in general, when you call printf, what's really happening is you're handing a bunch of characters to the operating system and saying, please print these to the screen. However, for efficiency reasons, slightly historical reasons, the operating system typically will not display those characters on the screen until it actually receives a \n as well. The idea being, years ago, it's kind of expensive computationally to print a character. So the operating system wanted to wait and do a whole bunch of them at once. Obviously, in this program, I want it to print without using a \n. So f-flush, which stands for file flush, this just means it's a message to the operating system saying, please, whatever I sent you, just print it now, print it now, print it now. In general, you don't need to do that, because in almost all of our examples, we've actually used \n. So this is a rarer case, but good to at least remember here. So in terms of documentation, you'll see a couple of things in the weeks to come. First of all, know that built into Linux and built into this command line environment is what's called man pages, manual pages. So that almost always, if you want to look up some technical details, you can type something like man printf for manual printf. And what happens once you hit enter is you get back a list of instructions here. And actually, this one's slightly a corner case. Let me do this. Man in chapter 3 of printf. And notice what I get. The Linux Programmer's Manual. And this is a little overwhelming, frankly, at first glance, which is why we'll show you a more user-friendly version in a moment. But long story short, this documentation, which we'll come back to later in the term, tells you, one, under synopsis, what header file you need to use this function. It mentions related functions. And these we won't get to for a while, and not even all of them. But printf, fprintf, sprintf, turns out there's a bunch of them. But if you ever want to know the precise definition of something, even if it's way more information than you care to know, it's almost always in these so-called man pages. Now, when we want you to look at here in PDFs of the problem sets, we'll generally tell you what to type, man something something, so that you don't need to go around guessing. But know that in the meantime, frankly, the more user-friendly thing to do is if you go to cs50.net and click resources, what you'll see on this page is a bunch of recommended resources. These are the free alternatives to the recommended textbooks, and typically, based on the week, we'll expand different parts to just draw your attention to things that we think would be useful. In particular, this one up here, C reference. Again, on the resources page, this is a fairly simple website that actually has much more user-friendly documentation for a whole lot of functions. Sometimes you have to kind of know what you're looking for because they're categorized here on the left-hand side. So I don't see printf immediately, but I do know that printf now is related to input and output, otherwise known as I/O. So if I click on CIO, there's a whole laundry list of functions we've never looked at, and most of these we won't even bother. Because you don't need to know all functions to make good use of a language. But there's printf. And if you scroll down here, okay, anything that says Bob is probably fairly user-friendly. And indeed, this is slightly more accessible descriptions of how it works. Now, some of the syntax we haven't gotten to just yet, but notice in this purple box, it's telling us standard.io.h. It's telling us that printf, and we'll come back to this, returns an int, even though we're not using this yet, just like main. And it takes a const char format, comma, ... So when in doubt, just kind of ignore for now things that you don't quite understand, but look for the examples in particular. And down here, you'll see a chart of all of the available format codes. We've talked about %d, we've talked about %f, but it turns out there's a whole bunch of others. And generally, only a few of these do you need, but know that this documentation, the C reference on CS50.net, is a wonderful place to start when you have questions, as well as any of the books that you might be dabbling in. So a few FYIs. One, Scratch is officially behind us. If you have Scratch boards at any point this week, just drop them with the TFs who tend to hang out in the front of the lecture hall. Lunch. You are all cordially invited to lunch this Friday and in future Fridays. If this is of interest, go to cs50.net, RSVP sometime today. Typically, we'll limit the number of seats to 20 or 30, just so that it's a reasonably intimate opportunity to chat with me, the TFs, the CAs, and we'll generally go somewhere in the square or in the house. So this Friday will be 1:15 p.m. if of interest, this URL, and we'll announce that in future weeks. So definitely some of you kind of forgot the section. So what we thought we'd do is, rather than turn the system off at noon today, 5 p.m. So please, if you forgot to section, at least get to the course's homepage. Click the link there to section before 5 p.m. today. Super sections. We filmed one last night. Super section is a temporary word for sections open to everyone. Real sections will start next week. The video from last night's appears online. If you'd like to go in person, they're today and tomorrow at 6 p.m. The rooms will be announced shortly on the course's homepage once the scheduling folks let us know. The walkthrough one was last night. That is online on the problem sets page. This is a walkthrough of the problem set standard edition itself. And now some fun facts. You submitted problem set 0, where we ask a number of survey questions, really to get a sense of demographics, and also just for fun, sort of geeky type things like what you have and what you use. So it turns out that 33% of you this year have an iPhone, 17% a BlackBerry, 17% an Android, 13% BlackBerry, and 33% of you are normal and just have sort of non-smartphones, and 3% have other, for some definition of other. Just if curious, 39% of you have AT&T, followed by Verizon, followed by T-Mobile. No one's using Sprint anymore, apparently. And then other is 4%. In terms of the demographics, so as is typically the case, sophomores are winning this year, followed by freshmen, juniors, and seniors. Realize, seniors, you're in very good company. There's almost 100 of you, so lest you feel like you're the oldest person in the room, you are not. We have folks, though, from GSAS, HBS, Extension School, and those local high schools, so we have quite the diversity of students this year. I was a little disappointed to see that Mather was nowhere close to number 1 this year, but Adams House has the most aspiring computer scientists. Followed by Elliott House, and then there's a lot of noise in there. So my own Mather did not win this year. Though in past years, the data might have been artificially inflated to make Mather win. So laptops, most of you have. This is not surprising. A few of you do indeed have desktops, but that's several hundred laptops floating around on campus. And then more technically interesting, here's the distribution of OSs, if you're curious. And if you're thinking you're the only one still running Vista, you're not. There are a few of you. And so here's a rough sense of numbers. Windows 7 followed by Mac OS 10.6, otherwise known as Snow Leopard. So just realize this is the diversity of operating systems. But when you aggregate it together, Macs are winning now by 56%, Windows 41, and Linux 4%. So more germane to 50. Let me send home this message. So we were really thrilled to see this in particular. Not only have we retained the same percentage of more comfortable students, those with prior programming backgrounds, been programming since you're 6 years old and the like, but also for the first time, the segment of those less comfortable is now the largest, and also is larger than last year's 46%. So this is wonderful, and we're so pleased to have all of you 55%, 35%, and 10%. And it is now our vow to keep you all on track and succeed by term's end. In terms of experience, too, lest you not believe what I say, 54% of you have no prior programming or computer science experience whatsoever, 41% little, and 5% said a lot. So a word now on piece sets 1 and onward. So, oh, no, on the CS50 appliance. So in the interest of warding off some FAQs, know that there is an increasing amount of documentation online. These URLs are cited both in the PDF of piece set 1 as well as linked on those pages. But this is the reference page where for any and all questions for installing the CS50 appliance. Know that this now links to this additional page that has a whole lot of troubleshooting tips. Essentially, almost all of the problems folks might have run into with getting the appliance up and running is documented there. There are very common things that people run into on Macs and PCs alike. So consult these URLs. And then lastly, if you have a PC, generally that's within a few years old, most PCs actually support something called hardware virtualization or hardware assisted virtualization or VTX or similar. These are just words saying that built into modern CPUs is the ability to run virtual machines particularly fast. So some of you have found when installing the appliance, it's just downright unusable because it's so slow. And that's because some manufacturers turn this feature off by default. So typically, if you go to the here, if you're a PC user and you're just finding the appliance is just deathly slow, something's got to be wrong because you've got a 2 gigahertz computer, lots of RAM, any program should run well. Go here, follow the instructions, and odds are you can enable this feature, at which point things just become much more pleasurable. On Macs, this is a feature enabled automatically by default. So this is only for Windows and Linux folks. Regarding grades now, as you might have seen on the second page of the PSET, and this will recur throughout the term, 50 grades problem sets fairly coarsely and as qualitatively as possible, whereby the TFs will really prioritize providing you with handwritten or typed qualitative feedback, focusing less on +1, -1, and the like. In fact, the 4 axes that we focus on when evaluating work is 1, scope, whereby we mean just did you do the PSET or did you cut a lot of corners, did you do half of it or the like, how much of it did you actually bite off. Correctness. Does it do what it's supposed to do? Or do you have 3% signs appearing in your program? Or are there other bugs? Correctness. Design is harder to define, and it's something you'll get better at over time. It's how well is your program designed? Do you have loops and conditions that are nested like 10 layers deep such that they're wrapping on the screen and you could have just done something simpler? Or is it nice and compact and elegant? And again, this is a message we'll send recurringly throughout the term that you'll get better at, but design again speaks to just not just does it work, but how well was it implemented? And that's where the qualitative feedback comes into play. And style, frankly, is one of the easiest things to get right, because all you have to do is mimic the style of code you see in sections and lectures. The CS50 style guide, which is mentioned in PSET 1, style refers to the simple things, like did you include comments in your code that tell you and the reader what you're doing? Did you indent your lines of code properly? Did you give variables nice names? And this is always the axis where people just throw away possible points, frankly, because it's sort of the last thing you think about, and so you just don't worry about hitting the spacebar properly. Honestly, not only is it good style, it also helps you chase down bugs. The worst thing to do is if your code is a big jumble of indentation and you're like, I'll fix that later, it's best to do it now, because if you keep things nicely and anally indented like I try to do in class, you'll actually be able to spot potential bugs and logical errors more easily. So do try to get into that habit. In terms of how we evaluate, it's really very coarse buckets, where 1 is poor, 5 is best. So early on in the semester, the target range for most students know is in the range of 2s, 3s, maybe some 4s, generally not so much 5s. But know that 3 is indeed good. It does not translate to 3 out of 5. That's 60%. Oh my God, I got a D on the first PSET. 3 is good. And the course has this abstraction between letter grades and numbers because, again, we do focus very much on the qualitative. So if I may, I have to put on a scary voice for just a moment. The course goes to great lengths in the syllabus and on page 2 of every problem set to emphasize the rules on academic honesty, which frankly essentially reduce to you're welcome and you're encouraged to talk about problem sets, go up at whiteboards with friends, discuss things in the D halls and the like, so long as those conversations are in pseudocode or in English, and so long as they stop at the point of actually communicating in code. The line is crossed when the conversation becomes, oh, can you send me your file? Or can I see what's on your screen? When the line is crossed again, when code, actual code, is involved. And again, just to send this message home, and it gives us no pleasure to cite these statistics every year, So this is a slide I keep updating every year, and it is the number of students this course alone has ad-boarded in the past 4 years. And it gives us no pleasure to give people mandatory time off from the college, but realize it happens only in these egregious cases where, again, the conversations have devolved into, oh my God, it's 2 a.m., just send me your code. And I'll submit that, or it's oversharing, or clearly you're sitting side by side typing up the same thing. Again, it's very easy to navigate these waters, and pedagogically, by all means, converse with classmates, whiteboards, dining halls, and the like. But again, the line is crossed per the syllabus and the fine print in each project when code is actually shared visually or electronically. OK, non-scary voice. Typecasting. So typecasting is this notion that we saw earlier of converting one type to another. But it's actually more useful than just these simple things of ints to floats and the like, because one of the domains we'll be focusing on this week is that of cryptography. And for those slightly familiar, what is cryptography in English? Coding, yeah, so it's the art of encrypting or scrambling information, right? So back in grade school, if you wanted to pass your crush a secret note and you wanted to hide it from the teacher, you might say like some message, but then you might rotate all of the letters by some number of places. So if you wanted to send the letter ABC to your crush, you would say BCD or something simple like that, but enough sufficiently complex that when the teacher grabs the piece of paper from you and intercepts it, it's not clear what it is unless he or she actually tries to decipher the actual encryption you were using back then. Now, thankfully, fast forward to modern day, you can do much more sophisticated things. And encryption is something we take for granted. Anytime you buy something online, every time you log into Facebook using HTTPS and ward off Firesheep and all of your friends trying to hijack your account, you're using encryption. Even things like the 33% of you with iPhones and 17% with Androids. Typically, the iPhone these days is automatically encrypted with a secret key. And so if your phone is ever lost and you enable that feature called remote wipe, where you can send a message to Apple and they can send a message to your phone that says delete it, all the phone is doing these days is just forgetting that secret key. And without that key, all it looks like is random zeros and ones to the bad guy that just stole your phone. So there's a lot of applications, just to very useful consumer things. And we'll introduce this weekend in problem set 2, this art of cryptography. And it pertains to a little something called typecasting in this case. I'm going to go ahead and open up ASCII1.c, another example that's been pre-prepared here that apparently does this. We've got a loop at the top, a for loop, then we've got some printf, then another for loop. And notice inside of each loop, this is just for demonstration purposes, I've hard-coded the numbers 65 and 26. Well, 26 is probably the English alphabet. What was 65, if you recall from last week? Yeah, so capital A. So this is just a simple little diagnostic program I wrote to show me what the number equivalent is of every character on my keyboard, at least the alphabetical characters. So I seem to have a loop that is starting at 65. It's not 0, but it's totally legit to start somewhere else if it makes more sense. I'm iterating up to 65 plus 26, so that'll get me all the way to Z, hopefully. I++, and now notice what's happening here. I'm printing out %C, which is a character, then a colon, then %D, and what am I plugging in? Well, notice I'm plugging in I both times, but the very first time I am, quote unquote, casting it to a char, because I want to actually see I, not as the number it is, but as the char, the character it represents. So I might see A, 65, B, 66, and so forth. And then take a guess here, 97 represents what? Lowercase a. So let's see this in action. So let me make this a little bigger. This is again called ASCII1. And ASCII, again, is just the acronym that denotes the code used to map letters to numbers and vice versa. So make ASCII1. Everything compiled OK. Let me go ahead and run ASCII. And indeed, it's a little long of a list, but if I scroll all the way back up, that's exactly what I had promised. So we can now see this conversion here. Now, what's the relevance? Well, again, think back to grade school. If you ever did send one of these silly notes, well, you had to rotate or convert letters to some other letters. Well, how did you really do that? Well, you shifted them by 1. A becomes B, B becomes C. But how do you express that? If you want a computer to do it, and do it way more sophisticatedly than a small kid could, well, you probably want to convert the letter, like A, to a number, then do your math, like +1, and then convert it back to a letter. Well, we already have that capability here. Let me go ahead and open up a variant of this. If I go and open up ASCII2, we'll see this. In ASCII2, I'm doing something a little prettier because it got a little overwhelming to have it all display on the screen. So again, just to mention, that format code I mentioned earlier, %3d means no matter what, use 3 characters here to represent a number and just prepend it with white space, just the spacebar character automatically. So what is this going to do? Well, this is just a different aesthetic. I'm going to go ahead and make ASCII 2. The code is almost exactly the same. And then I'm going to run ASCII 2. And what happens? Well, now I just get a chart. So again, fairly simple aesthetic modification, but it's a little more user-friendly now. But I wanted everything to line up. So notice again, %C, %D. But notice on the right-hand side, I actually said %3D. Why did I use 3D, do you think, for the third column and not for the first? OK, I couldn't make any of that out. But yes, I was probably correct. Right? It's because the numbers in the third column there actually are 3 digits potentially. Yes, you start at 97, 98, 99, but then you get 3-digit numbers. But for the capital letters, it was all single digits. So I could have said %2D, but it wasn't necessary because I know they're all going to be 2 digits. But that's all. So we're just now massaging the output aesthetically by using these disparate format codes. Well, let's see if we can't do something a little more interesting than just print out these letters. So this is not a complete implementation, but it is a demonstration of a game that you might recall known as Battleship. So Battleship, remember, actually, even if that sounds cool, you're going to be very underwhelmed in a second. So if I make Battleship and then run Battleship, that's all you're getting today. So we have the layout of a Battleship board. This is that like little game with the plastic board that's got all the holes. You put the pegs in and the little fake ships, and you say A2, and you sunk your battleship. That kind of game, if unfamiliar. Yeah. So I just realized how stupid I sounded saying that. So with Battleship, we have this opportunity, though, to format this output in a little interesting way. Right? I clearly want a grid of some sort. And I also need to be careful with like the number 10, because all of a sudden my grid could get screwed up because all of a sudden I have a 2-digit number. So just to see how we did this, let's scroll up to the code here. It's starting to look more complex, but it's just a repetition of these same constructs from before. So I'm first going to print the top row of numbers. So I print out \n space, space, space. And I just figured that out, honestly, by trial and error. I wanted a little white space, and then I wanted to indent the board a little bit. What do I do next? I want to print 1 through 10. And so here I have %D again and again. And notice a couple white spaces after each for aesthetics. So that's actually pretty straightforward. But now here, notice we have our first example of a nested loop, whereby I have an outer loop where convention says use I as your counter. So I is 0, go up to 10, I++. Notice now, what do I want to do? What am I doing here? %C. So remember, the output of this screen did this for me. I had all the letters of the alphabet on the left-hand side. Well, what am I doing then with this %C? That's how I'm getting every letter of the alphabet. Let me scroll this back here. Why am I doing A plus I? This feels a little weird. Yeah. Yeah. Exactly. I want to change the letter I'm printing on each iteration by adding 1 to it again and again. So A, I know, is going to be represented by some number. It happens to be 65. It turns out that even though in the previous ASCII examples I was explicitly casting, you actually don't need to explicitly cast. C and the compiler are smart enough to know that a char is an int, and an int is a char. At the end of the day, the only difference is how you interpret those zeros and ones. Now, how am I going to interpret these zeros and ones here? Well, printf is going to print a character. So it doesn't matter if I pass in a char specifically or an int. It's going to be displayed as a character. So I can now use this shorthand notation of start with the letter A, capital A, whatever that is, plus I to it, which initially is going to be 0. So what's A plus 0? It's just A, because it's 65 plus 0, 65, and it's printed as a char, so it's A. But on the next iteration, I is 1, and then 2, and then 3, ... 25. And so in this way, can I increment even letters of the alphabet from A to Z? Now notice this nested loop, so to speak. Nested in the sense that it's indented in inside of the outermost curly braces. So J gets 1. J is less than 10. What is this doing? This is just printing out 0, 0, 0, 0, 0. So what's really going on here? This is actually a very common example of using 2 nested for loops. If you want to print out rows and columns, you essentially need 2 loops, generally for loops by convention. And so the outermost loop is doing what? Iterating from right to left or top to bottom? So it's actually doing top to bottom. So the outermost loop involving I is top to bottom. and the innermost loop is doing the columns. And you can infer this again, because if I'm printing the wholes by using this lowercase o, that's happening inside the loop. And this makes sense, because if this thing's like a typewriter, you better start from the top and go right, 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 because the moment you go down, that's it. You can't go back and add anything to the previous line, as we discussed earlier with \n. So the outermost loop I is essentially going to iterate over our rows. But on each iteration of a row, we want to go dot, 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 dot from left to right to generate all of these zeros. Now, this is not by any means a full-fledged game. It's just the aesthetics of the board. And the very last line is just to print out some blank space. But it does demonstrate now how we can nest these kinds of things. So perhaps a little more familiar is this example here. So you might recall this incredibly annoying song from grade school as well, or school bus rides. So 99 bottles of beer on the wall. 99 bottles of beer, take one down, pass it around. 99 bottles of beer on the wall. I also felt stupid saying that. But there's the song that you might remember saying is from childhood. What's nice for our purposes today is that it's obviously very cyclical, which contributes to its annoyance. But it's also an opportunity to decrement this number again and again and again, while still doing a lot of the same thing at the same time. So let's see how this might be implemented at the end. If I make beer 1 and zoom in on this and hit enter, and then type beer 1, it's going to prompt me for a number. I'll say 99, enter. It's a pretty fast implementation of this song, right? We could make it really tedious by inserting sleep or something like that. But if I scroll up, I've indeed started all the way up at the top, 99, and counted all of the way down. So let's just see one way in which we can do this. So let me zoom in on my code. The very top says how many bottles of beer will there be, and then I use getInt. So this is kind of old hat now. Now here's a common convention. If the user does not cooperate, you could pester them again and again, but I decided just as a design decision, if the user's not cooperating, I'm just going to quit. And if you want to quit a program in C, you return a value from main, and you should return anything except what? 0, right? So 0 generally means success. And that should be returned by default at the end, or if explicitly by you, if all went well. But if something did not go well, like the user was just not cooperating, you should probably return something other than 0. And the convention is at least return 1. Or if you want to really have fine-grained control, return 1 for the first possible error, 2 for the next, 3 for the next, but anything other than 0. Now, if I don't return, I keep executing. So if the user did give me a positive number, I start singing this song. And how might I do this? Well, notice how we might structure this with a loop. So I'm first going to just print out a new line. Then I'm going to iterate from I equals n down to 0. So we did this before with our progress bar. And I'm going to print out %d bottles of beer on the wall, I. % bottles of beer, I. Take one down, pass it around. That's just the same thing. And now notice here's how I go from 99 to 98. Then the loop repeats. Then the loop repeats. Dot, dot, dot. But this is far from perfect. Where are some opportunities for improvement here, would you say? Yeah? Yeah, this is really me cutting more corners, right? And this is me avoiding the issue that at some point this program is going to get down all the way to the bottom and say 1 bottles of beer on the wall. And I didn't want to look like I'd made a bug, so I just parenthesized the S for 98 other conditions just to say, oh, now I'm handling both scenarios. But clearly we can do this better. We could have some kind of condition inside of this loop and say if I equals 1, print it as bottle, otherwise print it as bottles. What else could we do? What's that?
Just have the loop go to 1 and then have a separate loop.
OK, so we could have the loop just go down to 1 and then special case, as we'll see, the last chunk of this song and just print out verbatim 1 bottle of beer on the wall or 0, whatever the lowest case is that you might want to include. Any other thoughts? So you could even be a little more efficient than instead of conditionally spitting out one sentence or the other, you could just special case the S, print out the singular, and then just print out the yes, optionally, yes or no. So if I go back in here, let's see, beer, 1. The biggest number we can represent with an int is roughly 2 billion. Oh, damn it. All right. That's a command line argument. More on that next time. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Why don't we leave it there, and we'll see you on Wednesday.